Dear students, welcome YouTube channel Mathematics Students Helper. Now in this video we discuss ring theory. This is part 2. Part 2 is the continuation of part 1 and part 2 is a continuation of part 3. So you have to see part 1 as well as part 3, and there are another parts of ring theory. Link of that videos are given in description box. Please see that videos, then you get clear concepts about ring theory. However, please see the video and take your notebook and pen and exercise yourself. Here mainly I discuss about zero ring and trivial ring, and then I give some properties of ring, and at last we discuss about relation between zero element and unity. After watching, if you can understand my video, please like it and share it with your friends. If the channel is still not subscribed, please subscribe my channel to get more videos. Now at first we give the definition of zero ring. Suppose A plus be a abelian group or commutative group. Now we extend A plus as a ring. For that purpose we have to define a multiplication, so for which A dot will be a ring and distribution of multiplication over addition will be hold. Okay, for that purpose we define multiplication on A by A dot B equal to 0 for all AB in R, 0 being additive identity in A. That is, if you multiply two elements from A, then the result will be 0. Okay, here I define in that format. Now I will check A dot, that is the set A under multiplication, is it a semi group or not. For that purpose we can write then A dot B equal to 0 for all A B in A. That is, multiplication of two elements is in 0. Here see that there are two elements, arbitrary elements in A, and their multiplication is 0, which is also in A. Therefore we can say that A is closed with respect to multiplication. Therefore A is closed under multiplication. Now we have to check the associative property of multiplication. For that purpose we consider three elements. Let A, B, C are three elements in A. Now A dot B plus C, we calculate A dot B plus C. Actually we have to so that A dot B plus C, here B dot C is in first bracket, this must be equal to A dot B dot C. In that case A dot B will be first bracket. So please see A dot B dot C, here B dot C is 0. From the definition of multiplication, product multiplication of two elements is always 0. Therefore here B dot C will be 0. Therefore A dot 0. Here you see that A dot 0, this will be 0 because A is an element of R and as well as 0 is also an element of A. Therefore multiplication of that two elements must be 0 from the definition of multiplication. Now we consider the multiplication A dot B dot C. Here you see that A and B are in first bracket. At first we have to get that result and then multiply the result with C. Here you see that A dot B must be 0 from the definition of multiplication. Therefore this will be 0 dot C, and 0 dot C will again equal to 0 because multiplication of two elements of A is 0. So you see that A dot B dot C, here A dot B dot C equal to 0, here A dot B dot C is also equal to 0. So A dot B dot C equal to A dot B dot C for all ABC in R. So we can say that multiplication is associative on capital A on the set A. So we see that A is closed under multiplication. Here A is closed under multiplication as well as multiplication is associative on A. Therefore we can conclude that A dot is a semi group. Okay, now our target is to show that A plus dot is a ring, that is A will form a ring with respect to addition, given addition and our multiplication which we define here. We have to show that A plus dot will be a ring. For that purpose we have to show also distribution property. For that purpose we consider A dot of B plus C. A dot of B plus C, this will be 0 because you see that B and C are two elements of capital A. Therefore addition of that two elements must be in capital A, because we given that A plus is a commutative group, therefore capital A will be closed with respect to addition. Therefore addition of two elements, that is B plus C, must be in capital A. Therefore, here we see that A is an element in capital A as well as B plus C is an element in capital A. Therefore, multiplication of that two elements must be 0 because of definition of multiplication. Now, we have to show that this is equal to A dot B plus A dot C. This is equal to A dot B and A dot C. Now, A dot B equal to is also 0 from the definition of multiplication as well as A dot C equal to 0 from the definition of multiplication, because multiplication of two elements defines in such a way that product of that two elements must be 0. Okay. So, A dot B plus C equal to 0 as well as A dot B plus A dot C equal to 0. Therefore, A dot B plus C equal to 0 plus 0, that is A dot B plus A dot C. So, here left distributive law holds. Therefore, left distributive law holds. Similarly, we can show that right distribution law holds, and therefore distributive law holds in A. So, we see that number 1, A plus is a commutative group which is given, A dot is a semi group, and at last we show that distributive law holds in A. So, here A plus dot is a ring. This ring is called 0 ring. Okay. So, what is 0 ring? At first there are a commutative group with respect to addition, and then we have to define multiplication in such a way that product of any two elements must be 0. For that purpose we write this as 0 ring. Okay. Then we show that capital A will be ring with respect to two binary operations, binary compositions. One is addition which is given and multiplication which we define. Okay. This ring is called 0 ring. In particular, if we take B equal to singleton set 0, 0 being the 0 element in A plus dot, clearly B is a subgroup of A with respect to addition. Also, it can be seen that B is a semigroup with respect to multiplication, and that distribution law holds in B because all the elements A, B, C are 0 in B. So, B is also a ring with respect to B plus dot. That element, that set B, that is the ring B plus dot, is called ring. This ring is the trivial ring. This ring is called trivial ring. So, difference between ring 0 ring and trivial ring, what is this? Actually, trivial ring is a sub ring of 0 ring. This 0 ring means capital A contains more than one elements. It contains finite elements or infinite elements, but their product of any two elements must be 0. But in a trivial ring, the set contains only one element. This is singleton set 0. Okay, B contains only 0 element. Now we will show that in trivial ring, 0 is the 0 element as well as unity. Here 0 is, you know that 0 is the additive identity of the set B plus. Now we show that 0 is a unity in the set, that is 0 is also multiplicative identity. Since 0 dot 0 is 0, 0 dot 0 equal to 0, why? Because in a 0 ring we define multiplication in such a way that product of two elements must be 0. Here therefore product of 0 and 0 will be 0. So we can write A dot 0 equal to 0 dot A equal to 0 here, because we know A equal to 0 for all A belongs to B, because B contains only the additive identity, or B contains only 0 element of the ring capital A, 0 ring. Okay. So here this A all are 0. So 0 dot 0 equal to 0 dot 0 equal to 0. I put A in that place. I put A for the place of 0. Here is also so. A dot 0 equal to 0 dot A equal to 0. So we can show that if you multiply 0 with A, then the result will be A. So 0 is the multiplicative identity for that case. So in a trivial ring, 0 ring and unity are same. In a trivial ring, 0 equal to Y. Again you see that in a trivial ring contains, so trivial ring contains unity. Okay, trivial ring contains unity. Again in a trivial ring, A dot B equal to B dot A, because here A, B all are 0. So A dot B equal to 0 dot 0. Again B dot A is also 0 dot 0. All are 0 because from the definition of multiplication. So we can conclude that trivial ring is a commutative ring with unity. Okay. Later I will show that in general, that is in non-trivial ring with unity, 0 and I, that is 0 element and unity are actually distinct element in a non-trivial ring with unity. I will prove that theorem at last of the video. Now I will prove some properties in ring. Theorem 1. Here I prove some properties in a ring of elements. Suppose in a here in a ring R plus dot, you see that A dot 0 equal to 0 dot A equal to A for all A in R, 0 being the 0 element. If you multiply 0 with an element A in a ring, then the result will be 0. The product will be left or right, that does not matter, result will be 0 in every ring. Okay. And number 2 is A dot minus B equal to minus A dot B equal to that. Now there is single word. You see that in a 0 ring A dot 0 was 0 because this A dot 0 equal to 0 in a 0 ring. This 0 occurs due to definition of multiplication. A dot 0 equal to 0 holds in a ring when before proving that the 0 ring, before proving 0 ring, we use A dot 0 equal to 0 because that 0 A dot 0 means in the right hand side equal to 0. This 0 occurs due to definition of multiplication, but here I prove that theorem for every case because multiplication is not always defined in such a way that A dot B equal to 0 for all. Because you see in previous video you see that there are many rings. Suppose a set of real numbers, set of integers, set of rational number, set of 2 by 2 matrix, square matrices. We see that there are usual matrix here, their multiplication of two elements is not 0, is not always 0. Okay. So in a 0 ring, actually this is a special type of ring. We define a multiplication on the ring in special form such that product of two non-zero element or product of any two elements must be 0. Anyway, now here and the second theorem is A dot minus B equal to minus or A dot B equal to 0. A dot minus B equal to minus A dot B and minus A dot B equal to minus A dot B. Number 3, minus A dot minus B equal to A dot B. Okay. Actually all condition holds in a set of real numbers. Okay. These are obvious. You think these are obvious, so why we prove it? Actually it is obvious because I think these are obvious because we use that conditions in real number. Actually set of real numbers is a ring, so these conditions hold in a ring. Anyway, now I prove that theorems. At first we prove first theorem. Given that R plus dot is a ring, now we will in first proof. Here I write down A dot 0, A dot 0 equal to 0 dot 0, 0 plus A dot 0 plus 0. Just I put 0 plus 0 in the place of 0 because 0 plus 0 is always 0. This is the definition for additive identity or property of additive identity. Okay. Now here I use distributive property, distributive law. This will be A dot, you know that A dot B plus C equal to A dot B plus A dot C. This is left distribution property, that this will be A dot 0 plus A dot 0 by left distributive law. Now here you see that small a is an element of R and 0 is also element in R. 0 is the 0 element in R. Therefore A dot 0, this element A dot 0 must be an element of R. So A dot 0 belongs to R implies that minus A dot 0 belongs to R because minus of A dot 0 is the additive inverse of A dot 0. So minus A dot 0 must belong to R and addition of that two element must be 0. That is A dot 0 plus minus of A dot 0 must be 0 as well as minus of A dot 0 plus A dot 0 must be 0. Now we have to add A dot 0 in both sides of that relation. So adding minus of A dot 0 in both sides, we get in left hand side minus A dot 0 plus A dot 0 equal to A dot 0 minus A dot 0 plus whole that. We write this in under second bracket. Okay. Now this will be 0 and here just I shift second bracket. Here second bracket contain two elements of the two terms in last two terms, but by using associative we take second bracket between first two terms. So 0 equal to that. Here 0 occurs due to property of additive inverse and here this occurs due to associative property of addition. Again this is 0, therefore 0 equal to 0 plus A dot 0, that is A dot 0 equal to 0. Okay. So we find A dot 0 equal to 0. Now we have to prove that 0 dot A equal to 0. This is similar way. Here just I write down 0 dot A equal to here 0 dot A equal to 0 plus 0 dot A and then we have to use the distributive property. Okay. Here I use 0 dot a dot b, a plus b dot c equal to a dot c plus b dot c. Therefore 0 dot a plus 0 dot a, it occurs due to right distributive law. Again, by similar approach, 0 dot a belongs to R implies that minus 0 dot a in R. Then we have to add minus of 0 dot a in both sides. Adding minus 0 dot a in both sides, we get minus 0 dot a, just I add here minus 0 dot a plus that, I write this in second bracket, and as per previous portion, here this will be 0, and here bracket second bracket is shifted from first two elements by associative property of 0, and left hand side this is 0, and this occurs by associative property. Okay, again this will be 0, therefore 0 equal to 0 plus 0 dot a, that is 0 dot a equal to 0. Thus we get a dot 0 equal to 0 and 0 dot a is also 0. Therefore first theorem is proved. In second portion, we prove minus of a dot b equal to minus a dot b, and minus and a dot minus b equal to that also. At first I prove it, that is a dot minus b equal to minus of a dot b, and then I prove minus a dot b equal to a dot b. Okay, you see that here a dot b, here small a and small b are elements in R, but here minus b occurs, so we have to use some relation containing minus b. We know b plus minus b equal to 0. We know b plus minus b equal to 0. Okay, so minus b occurs, and you see that here is a dot minus b, so you have to multiply a in left side on both. Therefore a dot is equal to that, here I product a dot this equal to a dot, here in that place we put 0. Again this will be 0, because in part in number 1 we prove that a dot b equal to 0 and 0 dot a equal to a 0, therefore a dot 0 equal to 0. Here a dot b equal to 0 by 1. Okay, now here I use left distribution law, a dot b plus a dot of minus b. Okay, since a dot b belongs to R, we get minus of a dot b belongs to R. Okay, now we have to add minus a dot b in both sides, so we get, adding minus a dot b in both sides, we get a dot b of that, I write this in second bracket, therefore minus a dot b in third bracket equal to minus a dot b plus 0, because you see that in right hand side this is minus of a dot b, because this is 0. Okay, again here I use associative property, so minus a dot b plus a dot b in the bracket, and this is latter, this occurs by associative property. Here you see that minus a dot b plus b dot a dot b, I write down in together, and a dot b later, and this is minus a dot b, again this will be 0, therefore 0 plus a dot minus b equal to minus a dot b. Hence a dot minus b equal to minus of a dot b. This is 1. Actually this was 0 by 1, and here I use here a distributive property, left distribution law. However, this is 1, that is a dot minus b equal to minus a dot b, that is this is a dot minus b equal to minus of a dot b. Now you have to prove that portion, that minus a dot b equal to minus of a dot b. For that purpose we consider that relation. We have here we prove that we get a plus or minus a equal to 0. Now we take dot product multiplication b on both sides, because here b is right hand side of minus a, again this will be 0 by 1, again this will be a dot b plus minus a dot b, because right distributive law. Okay, this occurs by right distributive law. Since a dot b belongs to R, by minus of it additive inverse must belongs to R, and addition of that two elements must be 0. Now we have to add minus of a dot b in both sides. So minus a dot, adding minus a dot b in both sides, we get minus a dot b of that equal to minus a dot b plus 0. This will be 0, and here I used associative property for the purpose. A dot minus a dot b plus of minus a dot b, we write together. So minus a dot b plus a dot b in second bracket, and this element is there, equal to minus a dot b 0 means minus a dot 0. I use that by associative property. Again the terms in second bracket must be 0, because 1 is additive inverse of other. Therefore 0 plus minus a dot b equal to minus a dot b, 0 plus minus of a dot b equal to minus of a dot b, this means minus a dot b, therefore minus a dot b equal to minus of a b, this is 2. So in one we prove that a dot minus b equal to minus of a dot b, and here I prove that minus a dot b equal to minus of a dot b. So from 1 and 2 we get a dot minus b equal to minus a dot b equal to a dot b. So second part of the theorem is proved. Second part of the theorem means second a dot minus b equal to minus a dot b equal to minus of a dot b. Now we will go in third theorem under 1. This is minus a dot b equal to a dot b. For that purpose we consider minus b as p. You can consider minus a as a also. However, here I put p equal to minus b, therefore minus a dot b will be minus a dot p. Okay. Again minus a dot p means minus ap. From second theorem this will be minus a dot p. This occurs from second theorem. Okay. Now we put minus b in the place of b, the minus a dot b. Again minus a dot b means minus of ab. This also occurs from second too. So minus a dot b equal to here minus of, this is minus of ab. This occurs by 2. Again now we know that inverse of a element is actually same element. That is, we know minus x to the minus 1 x inverse whole inverse equal to x for every element x in a group. Here you see that minus of a dot b is the additive inverse of a dot b. Minus of a dot b is the additive inverse of a dot b. Again minus of terms in second bracket is the inverse of terms in second bracket. That is, whole is the inverse of a dot b. That is double inverse of a dot b. That means a dot b. So here a dot b is an element of the group. So additive inverse of a dot b is a dot b. That is minus of a dot b equal to a dot b. Okay. Additive inverse of inverse is same element. This is the additive inverse of that, and its inverse is that minus of that. Because additive inverse, so we write x inverse in the x minus x in the place of x inverse, because we take here the operation as addition. Therefore this will be ab. Here you see that minus a dot minus b equal to minus of minus ab. Here minus of minus ab means a dot b. So minus of a dot b minus of minus d minus of minus ab equal to a dot b. Hence third part of the theorem is proved. Okay, I hope that you understand this part also. Now I will go in some theorem where what is the relation between unity and zero element. This theorem states that, show that in a non-trivial ring with unity 0 not equal to y. That is, zero element and unity are distinct elements. Okay, it occurs in a non-trivial ring only. Non-trivial ring actually already it have to contain unity also. In a non-trivial ring 0 and I must be distinct, because you show that in a trivial ring 0 and I are equal, which I discussed before sometimes. Okay, before some moments. Here we have to prove that 0 equal to y. Let R plus be a non-trivial ring with unity. Actually trivial ring means it contains only additive identity. So non-trivial ring means it contains an element other than 0. Okay, so R contains at least one non-zero element. R contains one non-zero element, because in a trivial ring means R actually singleton set 0. Non-trivial means R not equal to singleton set 0. Since it is group, it is non-empty, therefore it contains some elements other than 0. 0 is already in that set, because R is ring. Non-trivial ring means it is also a ring. So 0 must be in R. Since it is not non-zero, so R has some elements other than 0. So here write R contains at least one non-zero element. Suppose A be a non-zero element in R. Now by property of zero element we get A dot 0 equal to 0. Here I prove it by in theorem 1 part 1. A dot 0 equal to 0 for every elements. Again by the property of unity we get A dot 0 equal to 0. Sorry, A dot I equal to I. A dot I equal to I from the properties of unity, multiplicative identity. Okay, now we have to prove that 0 equal to y. I prove it by contradiction. For that purpose, if possible, we assume that 0 equal to I. if possible let 0 equal to I. So a dot 0 equal to a dot I. 0 dot I means a dot 0 equal to a dot I. Again a dot 0 equal to 0. Therefore here I put 0. Again a dot I equal to I. So 0 equal to I. Sorry, 0 equal to A. This shows that A is 0. But we assume that we take A as non-zero element, but here A is 0. But so it is contradiction. So this contradicts the fact that A is a non-zero element in R. This contradiction is occurs for our assumption. Here we assume that 0 equal to I. So 0 must be unequal from I. Hence 0 not equal to I. That is 0 element in a non-trivial ring with unity. 0 element and unity are distinct elements. Okay. Okay. I hope that you understand my video. Please see part 3. This is actually part 2. Part 3 this is continuation, and you have to also see part 1 because this is the continuation of part 1. I hope that you understand my video. Anyway, thank you. Have a good day.